what if we didn't even have the tools to talk about there exists at some unspecified length a proof of false, right? And we wouldn't be able to say a system is consistent. Maybe we would be forced to say, you know, any proof of false. Yeah, maybe we'd be forced to talk about asymptotics, or maybe we'd be forced to talk about finite things.
Cody holds a PhD in computer science on the subject of termination of higher order programming languages and language semantics. He worked as a postdoctoral student in the Proval team, developing an interval analysis module for analyzing statements about floating point operations in the Alt-Ergo SMT solver. He also worked as a postdoc at Carnegie Mellon University on subjects related to type theory, then Draper Labs, doing research on program analysis Java Bytecode. Welcome to the James Wiles podcast.
All right, thanks so much for joining the podcast, Cody. I appreciate your time. There's a lot of interesting things to chat about here in the realm of mathematics and logic and even coding, perhaps. I thought maybe we can just start off with going through a little bit of your own history. You gave me like little snapshots of little things you had done in the past at various places. And a couple of those things really piqued my interest. So I'd love to dig into it a little bit, if you don't mind.
Yeah, of course.
So the first thing you mentioned there was about rewriting systems, and then there was a specific type of higher order rewriting you did where you introduced lambda expressions. Can you just touch a little bit on that, and like what was interesting about that that type of work you did?
Sure. So I think, okay, one of the dangers is that I get too much lost into the intricacies, but I'll try to keep this kind of short and sweet.
Okay.
So in the 80s and 90s, I think people were very excited about understanding systems of equations and how those could be turned into computation systems. I think, you know, equations have been studied since, you know, the dawn of mathematics, but then turning those into computation steps is sort of a recent, kind of a recent trend in mathematics. And at the time, I think people were excited about using computers to try and understand those things. And they had hope that this could be, you know, this turns out to be, you know, a Turing complete form of computation, which is not surprising because it's actually hard to not be. But yeah, how do we look at those and analyze those and understand those? And there were many results that came out, you know, of these studies. Some of them are, I think, still quite relevant today to like databases theory and, you know, other things, program analysis. Okay, but you know, there are some limitations. One of them is, you know, it turns out that rewriting as a coding paradigm is a little bit weak. You can't name pieces of terms and then abstract over them, which is something that's very tempting to do, to just be able to replace, you know, just something you see visually on the screen in programming and pull that out, replace it with a variable. That's what
that's kind of the identification problem. Is that kind of like trying to?
Yeah, it's sort of it's an abstraction
naming issue,
right? You want to say, hey, I can see something. Maybe it's a repeated form of like, you know, a program that I've written 5 times. I sure like to not write it a 6th time. I just want to replace that with a name or a placeholder and abstract over that. Say, hey, every time you see this name, it actually means something else. And okay, this is like a very important thing in programming. Rewrite theory doesn't naturally account for it. If you just add the ability to abstract to lambda, you know, if viewers are familiar with Python or, you know, many other languages, you can just take anything you see and turn it into a function.
Yeah.
Okay, but it turns out, again, and people in the 90s noticed this pretty quickly, this can be recast as a normal rewrite system, but that system has terrible properties. And if you add it sort of as a new kind of operator, a lot of the classical theory just breaks down. And so
can we define classical theory there? And going back to what you're saying when you're talking about the application of databases and coding, is rewriting originally wasn't designed for computers. This was just mathematics and people did it on pen and paper. And they thought this would be so cool just as a programming language, but this abstraction is the issue, right?
Yeah. I think so in mathematics, if you talk about groups or you talk about fields and rings and I'll talk maybe about this later, but Gödel had this idea of Herbrand and Gödel had this idea of defining computable functions. There's just a bunch of equations between things, right? Over the natural numbers or over the real numbers. This is very useful. Mathematicians all the time, they just want to say, hey, this equals this by some long string of equations. And each equation, like, you should be able to stare at it and see why it's true. And they do this all the time. And you can make at least in the early 20th century, you could make a great career if you were very good at writing a bunch of equations down and things like that. So mathematicians love this. Gödel originally based his notion of computation on this. And so, okay, so the relationship is already there for computation. And basically the idea is everything is either a fixed function or operation, and then inside are either other operations or variables, right? So recursively, you have definite functions, which people sometimes call first order. They have names. It's like the plus operation or the group multiplication, or subtraction. And then variables. And then basically an equation turns that thing into another such thing. And the equation morally represents two things that are the same in your mind.
So you've basically just described all of what now? Computation or all of mathematics? I mean, is that just
no.
is that rewriting?
Well, yes and no. I'm saying that this is what the first order rewrite theory is, and I'm saying that it's very powerful in the sense that you can do a lot with it. And if you use increasingly complex encodings, basically yes, you can do everything in it. But those encodings become unwieldy, right? Because maybe you're representing very abstract objects, or maybe you want to talk about things that are very generic that should be replaced by other things. So the classical theory of first order writing, first order equations, it is compelling, but it has limitations. And indeed, there's such a thing called equational logic, where the only thing you can talk about is universally quantified equations or qualities. And that's not what logicians use, and it's certainly not what mathematicians use. They talk about other things than just equations sometimes. And rewriting is, taking an equation and giving it a direction where you say, hey, if you see this one on the left, then turn it into this one on the right. And that's always a good idea. Today we know that it's not always necessarily that good of an idea. But still, this is a very natural thing for mathematicians to do, also somewhat a natural thing for computer scientists to do. For example, in a compiler, if you see 0 plus x anywhere in your program, then it would sure be nice if your optimizer just replaced that with x, right? Because, hey, you don't want, at runtime, you don't want to do plus zeros all over the place. So optimizers do this all the time. They apply these rewrite rules. In database theory, this happens as well, right? Basically, a database is a bunch of terms, morally, of this kind. A row is just basically a big constructor applied to a bunch of concrete things, like what department you live in and what your salary is, maybe, I don't know, in your name. And often you want equations to hold over these things, like a person's manager should be in the same department as them or something like that. And so in computer science, it happens all the time that you want a bunch of equations to hold, and you want to know if two things are equal. This is famously an undecidable problem. I don't know if I need to explain what an undecidable problem is, but I will later if we get around to it. But rewriting gives you techniques to turn this undecidable problem sometimes into a decidable problem, if you're lucky, right? Of course, you can't do it always, but sometimes you can say, hey, I have a bunch of equations. I have no idea how to prove these two things are equal. Hey, turn it into a rewrite system, do a bunch of rewrites, then just check whether you get the same object. And
so is that because you can use the power of computation to do it, where you just crunch everything that can be crunched and you don't have to apply reasoning or intuition. It just
yes,
reduces to something that then can you then
reason. Yeah, absolutely. Again, this doesn't always work, and this whole process of like turning a bunch of equations into a computation you don't have to think about can be a subtle one, right? Sometimes you really need to be clever in order to take a bunch of equations that you can apply in any order in any place into a set of rewrite rules that you know how and when to apply, and that will actually bring you to the same kind of representative. So I think this is an interesting subject in itself, which I wasn't intending to talk about.
Yeah, sure. Yeah, I just wanted to touch on that unique angle of rewriting or higher order rewriting. So was that just rewriting described now, or
that was just rewriting I described now? And then just adding lambdas to this thing, just adding the ability to abstract over a function symbol, right? So you replace the plus now by a variable, a higher order variable. And now you can say, oh, I don't know if this is plus. It's just some thing that takes in 2 inputs and returns an output. And maybe I then apply that whole thing to a plus, and then that reduces to 0 plus x. But I'm allowed to abstract over this whole operation. All right, that's a very powerful abstraction. It's a very useful one. But of course, now when you're trying to figure things out about how this equational system behaves, that's much harder, because now variables can represent.
It feels like it's almost everything can be made higher order. It tends to be like a trend in mathematics: higher this and higher order that.
I think there's something very profound here, and I'm not sure I'm qualified to like really say how, explain the profundity. But your ability to identify things that can be abstracted, and then building a system like a calculus or a logic system that allows you to abstract that thing, to turn it into a variable. I think that is a very, very powerful process. And it's almost essentially, the most representative thing of like what intelligence means. Your ability to say, hey, we know how to recognize one of these things, and we know how to think about it abstractly.
That's what I was going to mention, because there's this idea about intelligence being just compression. I feel it's a very important aspect of intelligence, but it seems to be quite an important aspect. In other words, just being able to take something that is outside the realm of your ability to compute things, represent it either symbolically as something that you can then hold within your processing power, and you need to be able to compress it or represent something symbolically, and then that compression can either be lossy or lossless, and that's an issue. But it seems to be something related to intelligence, or what we do as humans, very, very natively.
Yeah, I tend to agree. Of course, the devil's in the details.
Yeah. Okay, so maybe we'll just jump through the next step here. So then you went into something called pure logical statements, or you're working on something like pure logical statements.
Maybe I should check, but I suspect that what I said was pure type theory, maybe.
Oh, that was the next one. Yeah. So conservatancy in pure type systems.
Oh, I see. Okay. I think about this because it's a little bit related, right? Basically, pure type systems gives you a way. It's a framework. It's a framework of many different logics, but within that framework, you can identify this ability to replace something with its abstraction, and then you can ask, well, what? Okay, so what does that enable you to do, right? Does that enable you to express more things, and answer more questions, or just express more things?
So how would something, if you replaced it, give you more? Like, wouldn't the information you start with always have the most amount of information? Like, by replacing it something, can't you only ever replace something with like a lower information? Otherwise, you're introducing information into the system, right?
Yes. I think what I mean here is this ability to abstract itself, your ability to talk about these abstractions, allows you to ask more questions, right? For example, you know, just expressing that a function is always returns the same input, right? Just that ability to talk about abstractly every function of this type returns exactly its input, right? Just that ability to express that is not necessarily present in a first order system, because you can't even talk about all functions. You can talk about all integers, for example, but you can't say, hey, all these functions of this type, right? So if you add that ability to quantify, to abstract over all functions of, say, int to int, you're adding more things to say. You're adding
ability.
Right.
And like processing power.
Right.
You're freeing up processing power to focus on asking more questions.
And it can be the case in certain circumstances that adding this ability to quantify over functions, along with reasonable rules to reason about those things, gives you more actual proof power, gives you more power to answer questions in the original language, right? This is a common question in mathematical logic, which is, hey, we have a language, we're going to extend the language, give you more, proof abilities about this extended thing. Can I prove more theorems in the original space, right? Maybe this is actually a place where I would have drawn a diagram, but morally, yeah, you have a small bubble that represents your original statements. You extend the bubble to say I can say more things, and I can prove things about this extended realm. Can I prove more about the original realm? And there are cases where yes, you can. In fact, you can prove dramatically more about the original realm.
Is that almost like the analogy of saying with more knowledge you can solve more problems in a set system, like in a confined system? Like,
yes.
If you don't have the knowledge to deal with certain problems, you just don't know what to do with it.
Sometimes you need this additional ability to talk about new things, and that ability gives you the room, gives you the power to solve the original question. All right, and that's great sometimes. But often we want to say, oh, actually, no, I can talk about more things, but I can't solve more problems or answer more questions in the original language. And that's cool, because philosophically it tells you something. Philosophically, it means you haven't added more assumptions than you originally had. Maybe you can talk about more things, but those things somehow don't break your original kind of assumptions. And those original assumptions, right, they might be the only thing that you actually really trust, right? Maybe you don't trust that anything more isn't bad in some sense. And in logic, the worst thing that could possibly happen is a proof of 0 equals 1, a contradiction, right? And in the early 20th century, and I'm really kind of jumping the ball here.
Sure.
In the early 20th century, people were really nervous about our ability to formulate consistent mathematical theories. And so if you could say, hey, I have this theory, it doesn't allow me to talk about the things I really want to talk about, but it allows me to talk about things like consistency. And I add a ton of things to it, but I can't prove anything additional in this original bubble. Well, in particular, in that original bubble is the statement 0 equals 1. And if I can't prove 0 equals 1, then I'm still happy, right? And so that means that philosophically, what I've added here is only expressiveness, and I haven't diminished my trust in the system. All right. These kinds of extensions are called conservative extensions, and they're very much studied in all of mathematical logic. They're quite exciting, because you often want to talk about more things. You love to have the freedom to talk about more things, but you do not love that erosion of trust that comes with additional assumptions. You really want to be able to say, hey, what I knew to be absolutely the case or absolutely not the case in the original system is still there. It's still the kernel, right?
That's interesting. One of the initial discussions I had with a mathematician that's their kind of their sort of like full-time thing is when I was first exposed to these things, I only really like started paying attention to maths quite recently. When I was first exposed to these things, I was always trying to get down to like the basic like fundamentals, like what is the most primitive building blocks that you can reason about, and then build up to like, okay, then from there homotopy type theory and everything else like makes sense. And then he was saying that's not what mathematicians do. They love adding additional axioms because there's just more tools to use for. They don't care about the fundamental like core concepts that much because it's not necessarily practical for just getting to whatever the problem is that they're trying to solve at that point.
That's true.
So adding axioms is not an issue, but what's interesting about this, talking about these things and like having conservancy as an interesting primitive is the sort of statements that you can make that are analogous to like philosophical statements ends up sounding very profound. Because what you just spoke about there is like your ability to ask more questions with less assumptions, which is kind of like a belief system, which ends up having your trust in truth. And that's like, wow, that's like a philosophical statement. So you don't even need to worry about the math of it. Yeah.
And it really is. I mean, this is really the genesis of logic. I mean, people really cared about these philosophical questions, and they tried very hard to make those questions precise and, mathematical, I guess. And I think, I often argue, I don't know if I should stick to this argument, but I often argue that this is essentially one of the very rare absolute successes of philosophy, or at least analytic philosophy in this respect, which is they took this abstract notion of mathematical truth and consistency, and they tried to turn it into a mathematical calculus, and they succeeded. And this is very rare, right? They've often tried the same thing with, metaphysics and ontology and and ethics. They try to turn these into mathematical theories that they can agree on, and it invariably fails. It's very hard to agree on anything in these fields if you try to make them mathematical. But for the search of absolute truth in mathematics, they have, arguably completely succeeded. They wrote down a bunch of rules, and those rules are absolutely correct, and there's very little argument about them.
Would you say that is what maths is based on? Where you have I love this meme where it's like you have biologists, and before biologists you had chemists, and then before chemists you had like physicists, and then maths is supposed to be like always has been of everyone. But then I say like maybe philosophy is like before maths theoretically. Because it tends to, even in the practice of maths, it tends to be like what most people in it the mostly agree on is what ends up being truth, and that's almost like a philosophical.
Sure. So, so one thing I would say, my advisor at CMU is Jeremy Avigad, and he's thought about these problems, I think, more than I have. But I can certainly offer my opinion, which is that there are two things that mathematicians do, and those things are almost comically different. Okay. One thing is that they write down a bunch of equations and use logic, mostly formal logic, to prove things about these equations or about these objects, and they just provide definitions, lemmas, theorems, and pushing pencil on paper or typing them into a computer, and this all is this beautiful game of chess where everything is perfectly determined and every rule perfectly plays out. So in that sense, just the answer to your question is yes.
Okay, and just to talk about the motivation of that, is that just like adding to this system of consistency in like an increasing way? Like the more consistency you can just add to this consistent bubble, that is like its own objective in and of itself? Like, why are people doing this stuff? That's what I'm trying to.
Oh, why? The why. All right, but the why, of course, is the other thing, right? Is the other branch, right?
Okay.
So mathematicians indeed do not necessarily care what their system of axioms is, as long as it is consistent. Like that's really a necessary, right? You can't keep adding axioms willy-nilly if you create an inconsistency, right? So that's an important caveat to the mathematicians add axioms whenever it's convenient.
That's why I was asking earlier if that principle that the logicians came up with of consistency is what maths is based on, because that's kind of like the one axiom that.
Yeah, the one thing you do not want to add. But of course, it's hard to know if you've kept your system consistent. And two, mathematicians, they want to be able to prove the things that they think should be true, right? So often, yeah. So now we're in the second part, which is mathematicians don't actually care about any of that symbol pushing, right? They really don't. It's a necessary evil, right?
Yes.
What they want is to take objects that they can represent in their heads, things that they can build, that they have intuition about, and they want to understand those things, right? They want to know how those things work and what, answer very obvious questions, right? Mathematicians, of course, answer questions that nobody else understands. But usually a question that's been well studied by mathematicians is a question that is natural to other mathematicians, which is to say, if you're a mathematician and you see this object, it is very hard to not ask an obvious question like, hey, I have a system of polynomials that's cubic. That determines a surface, like in 3D space or something. Hey, how many lines can I fit, like straight lines can I fit on this surface? Is it 0? I don't know. This is a pretty natural question, right? And mathematicians have considered this question and determined that the answer is 27, and they've thought long and hard. And questions that are more abstract, right, are abstract to us, but to the people that came up with them, they look at these objects and they want to understand, and they have a natural question about it, or they have a natural feeling that this would sure be nice if it was true. And it's about this intuitive object that they have in their heads, right?
So it's an aesthetic appeal almost. There's some
absolutely. Mathematics is an entirely aesthetic subject. It is entirely driven by what people think would be sure, pretty, or nice, or elegant.
Which is really such a contradictory kind of thing.
I know.
As we earlier, because it's like mathematics is just
it's the only
especially when it's taught at high school,
complete objectivity, but the motivations are entirely subjective. And the beauty, I think, of mathematics is that yes, you have this subjective motivation, but then you get to have this objective, satisfaction, right? Where you know the answer once and for all, and it brings this kind of beauty that you can't even have, right, in other artistic endeavors, which is, hey, this painting is pretty nice, but yeah, I don't know if I got it right. Is it perfect? Who knows? Is it
once you've sold it, that's maybe the pleasure.
Is there any additional brushstroke that I could add? Or is it the right painting? Who knows? In mathematics, you get to know. It's great. And so that's why they put up with this horrible, logical formalism.
Okay, so what you're saying is mathematicians would have been artists if it wasn't for their wanting to have closure on the output that they create.
I think that's
something like that.
Statement. Yes, I think that's a very accurate statement.
Okay, that's very interesting. Okay, just you had a thought.
No, sorry, it escaped me.
Okay, so just to finish, kind of a little bit of the timeline there. You went from, and that was an interesting understanding of conservacy and pure type systems. Then you worked a little bit on program verification for timing attacks. So we can get a little bit on the computer sciencey side. Can you tell us just briefly what a timing attack is, and then how program verification can help with that?
Sure. This is a fascinating subject. I think it's probably the subject of its own
Okay.
But in short,
can I try to describe the time in attack part to see if I can summarize it very quickly?
Sure.
So you have user input, which is always unsafe, and you have a backend system. And sometimes what hackers will do is they'll time how quickly a response comes back from the backend to see if the backend is calculating something different depending on what input you're giving it. And that's how they can figure out certain passwords might be closer to the right one, for example.
Yeah, sure. Here's an example that's often used pedagogically. Imagine you have a password system, right? And the user that wrote that password system is, perfectly fine programmer, but they're not experienced. And so what they do is they take in your password, they take in the password that's expected, and then they look at the first character, and if those two characters are the same, they move to the second character, and if those two characters are the same, etc. Then as soon as they see a character that doesn't agree, they return with password denied. Great. As you can imagine, this is not ideal, because now I can try a password that starts with A, or just the password A, and if that gets rejected immediately, then I try B, and if that takes a little bit more time, then hey, the first letter of the password is a B. All right, and now it's like I always laugh in movies, because when they have a computer and it's looking for a password, it often finds the first letter of the password, and then the second letter, and the third letter. And that's exactly what you don't want. You don't want to be able to try one letter at a time, because that's very fast. And what's shocking is that this happens all the time. All the time we need to log into systems. All the time we need to do cryptography. All the time we need to do some computation that involves secrets. And all the time that computation really, really depends on the secret. How long it takes, how much power it takes, how much memory it takes, sometimes, of course, the response we give, but that's much easier to conceptualize.
So it's kind of like information leaking outside of your closed wall.
Correct. And so the question is, how do we prevent this? The answer is it's quite hard. But at the very least, you could say, okay, well, can we stare at the computer code, stare at it statically, and understand whether there's a chance for this to happen? In particular, that password example, you'd sure like to be able to take this simple loop that compares character by character and say, wait a minute, that loop runs in a number of steps that really, really depends on the secret. And that's probably not a good sign, right? If at least, you looped through the number of characters of the password, that still wouldn't be ideal, but at least that would always take the same amount of time, regardless of what the user inputted. And so this was a DARPA project, which is, I honestly cannot think of what DARPA stands for. Advanced Research Agency, maybe? Anyway, they were very interested in this problem for obvious reasons. And they had a big project of people developing various static analysis tools to try and do this at scale, which is a hard problem. Again, it's harder than some others.
And what's interesting with that is defense seems to be one of the industries that is most, or where I first heard about trying to program things with in a way that can be provable. And apparently certain fighter jets and stuff, all the code that's written for the fighter jet is written in a way where it's there's a provable outcome. I'm not sure if that's true, but that's kind of where I was first introduced to the concept.
Yes, so it's very unlikely that is true because of the scale of how much code is there. I think it's worth at least saying that in a fighter jet, probably there are on the order of millions of lines, perhaps hundreds of millions, and the order of how we can provide mathematical guarantees for code, that really depends on the type of guarantee you want, but I think for heavyweight guarantees of mathematically ensuring that the code does the correct thing in all circumstances, that's on the order of thousands or tens of thousands of lines. So you see that we're several orders of magnitude off, right, between the two, which is to say, just a sniff test tells you that probably that is not the case.
Interesting.
But
Okay.
yeah, the Army is historically a big consumer of these guarantees. But I think that we live in a world today where cryptography is so central to our lives because we're online all the time and because there's a lot of crucial stuff to each individual. And because, yeah, a lot of companies live and die by, for example, the cybersecurity of their infosec. That we've moved to a world where, and this is a good thing, where probably formal verification of code has become much more democratic.
And easier, or not necessarily?
It's become quite a bit easier. I think we've really lived through a silent revolution of how good we are at verifying code. Unfortunately, at the same time, we've lived through a revolution of how much code there is out there. And those revolutions have not necessarily been proportional, in the sense that the amount of code has increased, 100 or 1,000-fold. And our ability to verify code has gotten much, much better and much more easy to use and much more accessible, but not, with the same speed.
I've got a short side question, which might be too complicated. So you can tell me if it's too big of a tangent. But how far can just type checking or just introducing of types get you, or a proper type system get you to have verifiable, provable code? Is it like, could it theoretically be like everything you need, just throw like a super powerful type system at something, or it definitely is not enough?
Yes, I mean, yes, theoretically there is a language, some programming language and some type system for which having the correct type for a program is enough, right? That doesn't mean, but unfortunately, right, there's some abstract theorem of conservation of difficulty, right? Terry Tao often talks about conservation of difficulty, which says here that writing programs in such a language is necessarily going to be quite difficult. And essentially, as you write the program, you're going to have to give little bits of evidence of why your program is well typed, which turn out to be exactly the evidence you would need to give to say that your program is correct. So I think that's the short answer. In theory, you can just add enough types for it to be safe. In practice, I think there's a nuanced answer where you can say, hey, if I design my programming language correctly, like the way Rust, which is always a good example to bring up, the way Rust was designed was to have a type system which guides you to avoid certain errors and have certain guarantees, which the language is clever enough to make it a little bit easier. And you still have to work a little bit, but the language is helping you here.
I mean, the idea there is that you want to be able to cut out an entire class of problems, the same way that type scripts try to introduce a way to avoid an entire class of problems.
Sure, yeah. You want to cut out an entire class of problems. Now, unfortunately, if you want to take actions for which it is hard, the reason why that action is safe is hard to explain to a human. It's probably going to be hard to explain to a computer. And that means that it's probably going to be hard to write that program in a way that is type safe. And, notoriously in Rust, there are these uses of these unsafe blocks of code where really you're just saying, hey, I give up. I don't want to explain to the compiler that this is safe. A human's going to have to stare at this and very carefully know why it's safe. And so you want to fight a trade-off here, and you want to make the compiler smarter, and you want to make the human, well, the human is always going to make mistakes. So you want to make the human be able to offset that responsibility to the compiler to be clever. And you also kind of want to guide the human down the right path so they don't make a design decision that's going to bring them in a very awkward position.
Awkward, yeah.
Awkward in the sense they can write a correct program, but it's hard to write the program, and it's hard to justify the program.
So there's this interesting fact that I learned that the type system in TypeScript is Turing complete itself. Is that saying something about types mathematically, or just the implementation in TypeScript?
I think TypeScript made a design choice. I think that design choice was made somewhat deliberately. But I don't think that design choice is inevitable for any programming language, right? It is the decision that was made for TypeScript because TypeScript wanted to. I'm actually not an expert on TypeScript, so take what I say with a grain of salt. But I believe that the desire for TypeScript was you have a bunch of JavaScript programs. It would sure be nice if you could have a little bit more static trust, but unfortunately, turning JavaScript into a statically typed language is not possible. So we're going to add these somewhat sophisticated types that allow you to sort of push the bar a little bit more into the static world. And doing that requires a set of like somewhat subtle design decisions, I think, that result in this Turing completeness.
Okay, so it's not it's because when I heard that, I was like, oh, okay, maybe types is then just another, you know, whole mess of computational complexity that, you know,
it is, but it's I don't think
it's one of those things where it's like you add in more and hopefully you can say stuff more about the original set of things.
Yes. I don't think TypeScript is like a good exemplar of why it is hard to, you know, do type checking, for example, necessarily for a general purpose programming language.
Yeah, for sure. Okay, talking about languages in more detail, please tell me what is Daphne, because the reason I'm curious is that they've probably got the best logo of any computer programming language I've ever seen. I'm gonna put it up on screen, and what I love about it is that a lot of programming languages have this idea of having like quirky little like sort of not necessarily the most sophisticated, like definitely didn't pay somebody to make that logo for them as like a trend. Daphne is the quintessential best example that I've ever seen in my life. So.
I kind of love that logo. I have a complex relationship with that logo, but I agree, it's ridiculous. And it was definitely not. It was definitely not, a design team, that's for sure. I'm not sure what to say other than I always think of Roux. So Roux and Leno, I think, was the main creator of the language, and his hair is a little bit crazy, and that logo always reminds me of his hair. I'm not honestly sure what it's supposed to represent, though I've asked before, but I forget.
It looks like a waterfall, isn't it? Just
it looks like a waterfall, but I'm not sure. It's ridiculous, and it's almost, it's almost so outrageous that you can't help but like it.
So what is it? So is it a formal logical language?
Right. So I think its own web page would say it is a verification aware language. But like many languages I've worked with, but very rarely can you have a language which allows you to express intent of a program and also write the program and then check that these two things are conforming, right? What you want to do is say, hey, this is what I want to have happen when I run this program, and here's the program, and you should give me tools to help me justify that fact, which is this program actually has this contract.
But isn't there another component where it's, you also need to make it easy to compute things? Because Lean, for example, gives you, you can do your assumption, and then it helps you verify, that the structure of something is like proven to your assumption. But then it's a bit harder to actually like compute stuff in that structure.
That's fair. I mean, the way that Daphne verification works is that it's backed by some intermediate language, which I will not talk about, and then some SMT solver. So I haven't talked about SMT solvers, but they are basically a push button logic theorem prover, right? They ingest statements and they output yes or no. Now, internally, they're very complex, but externally, that's somewhat simple, right? You ask a question, you get a yes or no answer, right? And
no unknown, no unsolvable things. It's always yes or no. Is it binary?
Okay, so no, it answers yes, no, or I don't know is the short answer. The long answer is that SMT solvers are carefully structured in a way that if you ask a question in a certain form, then it will answer yes or no, right? If you ask a question in a certain form, that falls into the decidable fragment of the SMT solvers. And that decidable fragment is already very, very powerful. And you can ask a lot of very interesting questions. And there you basically have a guarantee that the program will return yes or no, with some additional caveats, which I will not go into right now. But anyway, SMT solvers, a few years back, people were saying SMT solvers are a disruptive technology, which is to say, like AI in some senses, the progress has sort of been linear. But the threshold at which they become vastly, vastly more useful was just recently crossed, right? So you have this upwards direction of how SMT solvers go. And then you have this line of like, below this, it's pointless. And above this, it's really quite useful. And SMT solvers basically cross that threshold, people argue in, 2005 or so, and have since then just gotten way better. So Daphne is backed by such an SMT solver, and Lean is not. And there's a complex discussion to be had here about what the trade-offs are. But at its coarsest, Daphne, if you express the obligations of the programs in this language that SMT solvers are very good at, then it uses that SMT solver and it requires very little additional effort by the programmer to convince it that the contract is being respected by the code. Lean does not have this capability in the same way, though arguably the automated theorem proving capabilities of Lean have gotten very good, and it's starting to approach this kind of level of automation that you can get with an SMT solver.
Interesting. So the automation might be able to make up for the deliberate construction of possible statements that you
This is typically the trade-off that you're always going to have to live with, which is I want to express complex things about my program. I want to express them in this larger language that allows me to express complex things. But now it is much harder to convince a verifier that this statement is true.
Would it be a correct analogy to say that's kind of like the approach between Stockfish and AlphaZero, where like Stockfish is kind of like deliberately finding instructions and heuristics that are like formally constructed, whereas AlphaZero is just like optimize for winning a game and then just do it with like as black box as possible? Or is that not necessarily quite accurate?
I mean, I'm not sure how to respond here. I do think that Stockfish and AlphaZero, to the extent that I know anything about them, have an SMT solver like quality to them, which is you want to ask a question, you get an answer, right? The SMT solver is, is every number even or odd, say, or is every number even? You get an answer. It's yes or no. Stockfish is, I have this board. Tell me what the next move is that I should make to optimize. And AlphaGo, it's the same, right? It's question, answer, very little human thought needs to go into it, right? An analogy here would be tougher to make, but it would imagine a chess tool where you have to explain what strategy you're making and what piece you're trying to capture eventually next, right? What's the next piece you're trying to capture? And then maybe the tool will think and say, okay, well, maybe this. And then you're like, no, that's probably not a good strategy. And so you'll try something else, right? This is, Lean is much more interactive, right? But human gets a lot more input. I would also have to say, for the sake of honesty, SMT solvers are black boxes in more ways than one, right? In one way, they question answer, right? And another way, SMT solvers themselves are pieces of software that might have bugs in them. And they're quite complex pieces of software that regularly do have bugs in them. Whereas Lean is constructed in a very careful way so that the only simplifying a little bit, the only piece of lean that really needs to be trusted is this tiny, tiny little bit of super optimized code. And that bit of code has been quite scrutinized. And what it also does is when you prove something, right, it gives you a yes or no answer, which is obviously yes if you've proven it. But it also gives you evidence, right? It builds an evidence, datum, which is called a proof term. And that...
But don't you have to construct that yourself? It just tells you if your term
well, the interaction you have with the machine is going to result in that construction. But the interaction you're having is at a much higher level than actually constructing the proof term, right? The proof, I mean, of course, you can give pieces of it, but Lean is going to do a ton of proof term construction. Indeed, a fun game to play is looking at the proof term after you've done a proof and see how huge it is compared to what you've written down.
See the full
yeah,
term,
the full proof.
yeah.
And that thing is a piece of evidence that you can put in a database and stare at later if you're all of a sudden not so sure anymore about whether that theorem was true or not. Whereas SMT solvers, no, it answered yes, it answered yes. That certain version, then maybe that version had a bug, right? Who knows if that bug was triggered?
Interesting.
So, okay, so this consideration, I think, is non-trivial in the design of Lean. And so part of that trade-off of like how much interaction you need is because, hey, it takes quite a bit of effort to construct that evidence. Now, in theory, SMT solvers could be constructing that evidence because in theory, everything SMT solvers do is sound. And so that evidence should be out there somewhere. But in practice, it takes time and energy, and it would make them less efficient. So far, I don't think it's the norm for SMT solvers to produce that evidence.
That's interesting.
But there's a convergence, right? Like I always think that when people are trying very hard to do the same thing, they will often start at the same point and then branch out and then come back together after a long period of soul searching.
That makes a lot of sense. I was playing around quite a bit with this concept called a reified input-output language, which was used in situations for computational law. And the idea there is you can construct situations and things that happen. So you have like facts and evidence that come in. It gets processed a little bit, and you basically have these institutional laws, which are either permissions or obligations. And the whole idea of that is given any set of facts, it will output permissions or obligations, but it will tell you exactly the chain of reasoning that it went through. And that's different to programming, where you give it input, it disregards all the intermediate steps unless you print into logs, which is a byproduct. It's not the actual function itself. And then it gives you an answer. So having this full chain is like sitting in a court case and saying, okay, we've got to this ultimate conclusion, but here's the entire process of how we got there. So
this sounds like a rewrite system, by the way.
Okay.
But
because that's what you mentioned, it's directional, right? One thing leads to the next. Yeah.
But something that does come to mind is, hey, with AI, we're facing this similar issue, right? Where AI is going to say, oh, you know what? You asked me a question, about law, or about, medicine, and here's an answer. And it will, it has this characteristic confidence of the answer, which I like. When I go to the doctor, I don't want the doctor to be like, I want them to be like, this is what's going on. But I also know that the doctor can internally assess their own confidence, right? And with LLMs, we're building them like SMT solvers, right? They're black boxes that take input and produce output. And yeah, you sure could log everything that it's doing, but that is useless to a human, right? It's just a bunch of like, it's too much.
Not explainable.
Also, it's not in a form that tells you anything, right? It's like, hey, this neuron was activated roughly. Like, I don't know anything about LLMs, but roughly, training data resulted in this abstract thing that you don't really understand, and these abstract things combined in some horrible combination to produce this output. Good luck. And I think this is definitely a problem, right?
that was the context that I was looking at it, because the idea was, could you use computational law as a way to regulate artificial intelligence decisions? So in some hypothetical future where AIs are kind of like making most of the decisions in your day-to-day life, it would be nice if you had contractual like structures with which it's a law in terms of how humans have developed law for thousands of years now, but the AIs are beholden to it somehow computationally. That was the idea.
Yeah. I think this is a natural question that many people are asking nowadays. I think this is a challenging question. I tend to be a pessimist, I think, in terms of what I believe is going to happen or what humans are incentivized to happen. But in this case, let's see, pessimism dictates that it is a very hard problem, right? Like there's a reason why laws are written in English and not written with a bunch of rules. And part of that reason is that it's hard to write these rules. These rules are hard actually for humans to understand. And even if they were easy for humans to understand, it's very likely that these rules taken together would be contradictory in some sense. Like law has this slight give to it. And sometimes it doesn't, but often there's a situation where something called the letter of the law would dictate a very harsh sentence, or two contradictory sentences, right? One is, thou shalt not be prosecuted, or thou shalt always be allowed to do X, and thou shalt never be allowed to do X, and that X is the same action, right? And then, maybe it goes to a higher court, and the higher court needs to make a judgment call. And that judgment call, man, it is, as we now unfortunately are keenly aware, is very much a somewhat opaque process as well. But at least it's being made by humans with the same kind of, hopefully, the same kind of empathy and emotional kind of nuance that we have.
That's what you're hoping. And I mean, the corollary of the letter of the law is the spirit of the law.
Right.
And yeah, that's kind of a decision. Are you taking the letter of the law or the spirit?
And this spirit versus letter, right? This happens a lot in mathematics, right? Where, you have this notion that you want, the semantics of the thing you want to capture, and then you have the formalism by which you capture it. And well, not to force the transition too much, but in mathematics, you can prove, for example, if you define in a certain specific way the spirit versus the letter, you can prove that these two things are adequate with respect to each other. But of course, in law, that'll never be possible. We don't have good ways to capture the spirit without capturing.
Is that a function of human language? Is that a function of the design of human language?
It is. I think it's also a function of the complexity of both the world. The world is insanely complex, and so we make enormous simplifying assumptions when we try to capture anything. And B, ethics is a subtle thing, and it's something that depends on time and place and person. And so, hey, we're trying to capture something that, maybe it's an English language problem, but also it's just a nature of ethics problem, which is, hey, you ask two different people in the street, they're going to have different opinions about what is just or fair.
That's the problem with AI a little bit, is because at some point the expectation, I guess, is AI has to make some kind of ethical, moral judgments if you want it to be responsible for more and more of what we would do on a day-to-day basis. And I think the idea there is law is just the closest thing we have to helping, judge those things. And if it's a way for AI to be beholden